Thank you very much. Thank you very much for the organizers for inviting me here. First of all, I have to say a word of caution. So at least in my first talk, there will be no multiple ergodic averages. Actually, my whole talk, there will be no multiple ergodic averages. And in my first talk, there will not even be ergodic averages. I think the original idea of Ergodic by inviting me was that I should give a promotional talk on the book that with co-authors was recently published on operator theoretic aspects of ergodic theory. Now it's very common to have non-conventional, non-standard, and other non-negative objects in mathematics. So this will be a non-promotional talk. You have to decide whether you actually. So I would not be very promotional, but of course, if you want to have a look at this book, I have it here, so I can lend it to you. So my contribution to this area here are sparse, and it's more. I share with you the view that I, as a functional analyst, have on certain things that I encountered in ergodic theory. So it's whether it will really contribute to the problems you are pondering. I cannot guarantee. It's just my view on certain things. Also, this view is not new, and everything that I'm saying here, although it might be new for you, or some of you, it's not new as part of the body of results or common knowledge in mathematics. So let me start first with a distinction between base space dynamics or state space dynamics and operator dynamics. So in state space dynamics, so that's state space dynamics, you have a set, you have a function phi, which to distinguish between operators and base state space functions, I write them phi and not t, but t is for operators. So you have a state space, a set with certain structure. You have a map which preserves the structure. So for example, topological dynamical systems, compact spaces, and the structure phi is continuous, or probability spaces, and phi is measure preserving. You can think of other structural features that you can preserve, of course. And in operator dynamics, you have a Banach space and you have an operator, a linear operator, and the Banach space may have additional structure, and the operator should preserve this additional structure. Yes, so so my view is, as a functional analyst, I want to study state space dynamics through operator dynamics. And therefore, I switch the category, so to speak. So if you know about category theory, so this is you switch from the state space category to operator category, to category of certain functional analytic spaces and operators between them. Now, when you change a category, then your notion of isomorphism changes. So first of all, I would like to say a few words on the notion of a homomorphism and the isomorphism notion that are somehow lurking in the background of these two distinct worlds. So this is my first let's go like this. That's homomorphisms of measure spaces. Of measure spaces or probability spaces. Well, the point is also, since you are from a probability background, you may not have, we may not share the same terminological common sense, so to speak. So as I don't understand much about Gibbs measures, and this comes here like as everybody knows, so I also have to introduce terminology before I can actually state some theorems or prove even some theorems. So what would a homomorphism of a measure spaces be? Now, in my notation for a measure space is always I have a symbol, a central symbol for the whole measure space, and then associated with this, the measure is denoted by mu x, the sigma algebra underlying is denoted by sigma x, and the same for y. So I do not have to introduce new symbols all the time for mu, nu, lambda, rho for measures, and so on. So also integration will be just integration over x, and so on, and it's clear what I mean. So a homomorphism of two measure spaces would be a measurable map, measurable and measure preserving. That would be a homomorphism. But already here, so the associated notion of an isomorphism would be, okay, it should be, you should have another homomorphism back from that one to that one, and composing the two should be the identity here and the identity there. So that would be the right categorical notion of isomorphism. But that's not the isomorphism we are interested in, because actually, usually in probability theory, we disregard null sets. So actually, we're only interested in equality almost everywhere. So also here, the notion of homomorphism already leaves the original category of measure spaces by identifying two of these maps when they are almost equal everywhere, when they are equal almost everywhere. So now this is the notion of homomorphism or isomorphism of measure spaces. Now when you go to the functional analytic side, then you associate with X the various LP spaces. And now you have the space L infinity X incorporates more or less the whole structure of the measure space modulo null sets. So if you forget about null sets, if you identify, then L infinity of X captures the whole information. So L infinity X has rich structure. It's a C-star algebra. It's commutative. So unital, actually, there's a one function. Unital C-star algebra, a commutative one. And it also has a lattice structure, so it's a Banach lattice. So that means, lattice means that on on real functions you have a canonical ordering, and the order is compatible with a norm in a certain way. So the Banach lattice structure is more or less determined by the absolute value mapping, which is defined pointwise almost everywhere. So if you know what the absolute value mapping does, you know the lattice structure. So that's the structural feature that characterizes lattice structure. Then apart from the linear structure, the algebra structure is multiplication and C-star is conjugation, and okay, the one function is in there. Okay, these are the functional analytic features, and then you have an integral. The integral is a map here from L infinity X plus, so from the positive elements to the extended positive real line, and together with this integral notion and these structural features determine the whole measure space. So if you apart from null sets, so if you know this as these functional analytic ingredients, then you know the measure space up to null sets. That means, so here the notion of a homomorphism. let me say what that is. So if you have a homomorphism of measure spaces, then you get the Koopman operator that reverses the arrows, of course. And this Koopman operator, so T phi f is just f composed with phi, preserves all the structural features. So it commutes with the integral. It is a C-star algebra homomorphism. It is a Banach lattice homomorphism. So all the structural features are preserved. So this operator is linear. So I write it here is linear. And the second one is one preserving. So it's unitary, so to speak. It preserves the constant function 1. It's multiplicative. The fourth one is lattice homomorphism. That means that so it commutes with taking the absolute value. I mean, this is all easy. I mean, it's just because everything is defined pointwise. So it's integral preserving. So that integral preserving, that means that that if you take t and then all the positive functions and then you integrate, it's the same as integrating y. And the last one is it's order continuous. What does that mean? That means if fn is a sequence that converges to 0 in the sense that it decreases and its infimum in the lattice structure is 0, then this is also true for the images. Yes, I mean, you may think of this in a pointwise almost everywhere manner, but you can rephrase this just in terms of the order of the structural features of the space. Gosh, this is warm here. So, sorry, I'm getting my voice getting. So, let me call an operator between L infinity spaces a Markov isomorphism, a Markov a Markov embedding, excuse me, if it has these properties. So this is a Markov embedding in my terminology, although the word Markov is overused in this context, of course.
There is necessarily a phi if you have such an operator?
No. So the point is, if you have a state space map, then you get such an operator. But in general, you can just write down these kinds of conditions on an operator and then call such an operator a Markov embedding. So each Koopman operator is a Markov embedding. It does not hold vice versa. So if you have a Markov embedding, it need not be a Koopman operator. Yeah, exactly.
There are
examples where you cannot go back. Yeah. So
even if you have out space.
Now up to isomorphism, up to the right notion of isomorphism, you can do. I will come to that. But so the message is actually that okay, if this would be an isomorphism of measure spaces in the sense that you have an inverse here, almost everywhere inverse, then of course this operator here would also have an inverse. And then this T would just be a Markov embedding which is surjective, and the inverse would also be a Markov embedding, which is also that's very easy to see. So that would be a Markov isomorphism then. So Markov isomorphism is just a surjective Markov embedding.
Embedding and factor are more or less the same.
Embedding and factor are the same, yes. We'll come to that. Markov isomorphism. And the notion of a Markov isomorphism is the right notion of isomorphism that one should employ here, because actually everything that you want to formulate, every theorem that you want to formulate, is invariant under Markov isomorphisms. So even almost everywhere convergence and all these kind of stuff that you usually formulate, because this is order continuity. So so this is the right notion of isomorphism in this category. Such a Markov embedding, of course, extrapolates to L1 spaces by just looking at, so L1 is the set of positive elements with finite integral, then you get the corresponding L1 space. T will be an L1 isometry, so T extends.
Why is Markov? Because coupled operator is Markov operator.
Yeah, well, not every Markov operator is a Koopman operator. That's why I don't call them Koopman operators. So because it does not have you could say a formal Koopman operator. A formal Koopman operator has the functional-analytic properties.
Okay, but I'm asking why you call it Markov embedding, because Koopman operator.
Yeah, because it's one preserving and it preserves the integral, and that's usually, so I will introduce the class of Markov operators afterwards, or bistochastic operators. So these are special ones of this class. So T extends to an isometric lattice homomorphism on all LP spaces. Okay, so this is the right notion of isomorphism, or my notion of isomorphism. This is the notion of embedding. Now, let me come to the second point here. That's dynamical systems. So now, up to now, there's no dynamics, only probability theory or measure theory, dynamic systems, and factors. So let us confine to probability spaces now at the moment, or no, not from now on. Let's say X and Y and so on are probability spaces. Then actually, a lot of things are redundant here. So for example, the information of T can be considered an operator on L1, and of course it comprises the operator on L infinity, because T is a positive operator and 1 is preserved. So L infinity is invariant. So then one consider as an operator on L1. So L1 to L1. Then the order continuity is also automatic. So this is only order continuity. You only have to incorporate in the general definition if your measure spaces are not finite. In finite measure spaces, order continuity is here for granted. So dynamical systems. Of course, a concrete dynamical system would just be a homomorphism of probability spaces where X is equal to Y. So here, now, an abstract dynamical system is a pair where you have a probability space and some Markov embedding from L1 to L1. So X is and T is a Markov embedding. And I will always write T for dynamics in the following. Always for all spaces, T is always the dynamics if I'm considering if I'm considering a dynamical situation. Now, what is now a homomorphism of dynamical systems? Now, the notion of homomorphism, I could actually write there maybe. So what is a homomorphism? So this would be a factor in the conventional terminology. Well, if you have a dynamical system here and you have a dynamical system here, and then phi would be a factor map if it intertwines the dynamics. It's measure preserving and it intertwines the dynamics. So what is the functional analytic equivalent of this notion? Now it is so you have two dynamical systems. So I should write here y to keep it consistent. So S would be, so S is a Markov embedding that intertwines the dynamics. So ST is T is TS. Okay, so this is the right functional analytic equivalent of a factor map. Of course, as in the as I said, such an operator need not be an actual state space factor map, but for everything that you want to study, that notion is good. I'm sorry, but this gets so warm. I just can't do this. I hope. This is really getting hot here. Okay, so if you have such an embedding, then of course you can. You can view. So S is an isometry. So somehow it embeds really L1 isometrically into L1 of X. So that is a subspace of L1 of X, but it's not just a subspace, it's much more. And this is the characterization of factors that I'm now discussing in a short couple of minutes. So here's a lemma. So the lemma says the following. So if you have a closed linear, well, you have a closed linear subspace of L1 of X, then the following assertions are equivalent. So the first assertion is F is the range of such a Markov embedding The second one is actually F is the L1 closure of some algebra R for some unital star subalgebra of L infinity. The third one is that it contains the one function and F is a sublattice, which by definition just means that it is invariant under taking the absolute value of a function. So that means if F is in F, then also the absolute value of F is in F. So it's invariant under taking absolute values. And the fourth one, that's the probabilistic characterization of it. So F is just L1 of X with some other for some sigma subalgebra of sigma x. So this is something that every probabilist knows. Of course, you have a sigma subalgebra of the L1 space, you get a subspace. The L1 space is embedded into the original L1 space. Now, I like these two characterizations, of course, because these are functional-analytic characterizations of this notion. Okay, let me see what is trivial here. So, of course, if 4 holds, then 1 holds, because you can just take this space and just take the inclusion map. That is, of course, a Markov embedding. So, if you have a Markov embedding, then you restrict it to the L infinity space, and then its image will be in a star subalgebra, because a Markov embedding is multiplicative, so you get a star subalgebra. Now, here comes the miracle. If it is actually the closure of a subalgebra, then it is also invariant under the absolute value mapping, which you might know from the proof of the Stone-Weierstrass theorem in functional analysis. There, a similar argument, or the same argument is used. And if you have a sublattice, then you can just consider those sets in the sigma algebra such that the characteristic function on that set is contained in the sublattice. You prove that this is a sigma algebra, and you prove that this is actually the sublattice. So for a functional analyst, the substructure that we are actually looking at are the sublattices that contain 1. So the closed linear subspaces which are invariant under the absolute value mapping and contain 1. And I will call this a probability subspace of L1 of x. So you see I'm building up a category here of L1 spaces, so to speak. L1 probability spaces. So let us call this, I call this a probability subspace of L1 of x. Okay, now if you have, so this is just characterizing the image of S in here. But now, what does it mean that the dynamics that it's intertwining? Well, it just means that this range here is invariant under the dynamics of T. So the factors, that means kind of the homomorphisms that you can build are the T invariant probability subspace so. Okay, after a while, when you're working this business, you get tired of always writing L1 of x, because you have to write 5 symbols, 1, 2, 3, 4, 5 symbols for one compound object which you're actually interested in. So eventually you will write x just for the space and not for the L1 space. But I will not do this here. So, actually, really, when you work in functional analysis, of course, you want also in every discipline, I think, you want for the objects that you work with most, you want the most simplest symbols, because you don't want to write always long chains of characters. So eventually, it's not at all important what x is. It's just important what the space is. And so eventually you will change notation. But that, of course, this is also very conventional and and one cannot just change conventions just like this. Okay, short. What is the clock? Okay, so then the next, the talk is about operators in ergodic theory. So I told you about Markov embeddings, Markov isomorphisms. So now let's say what Markov operators are. So suppose you have probability spaces, as always. So what is a Markov operator? And here also, I mean, as I said, Markov is overused and in different, with different meanings. So here, it's more, one also could say a bistochastic operator or bi-Markov operator, depending on the background that you're from. So it's a positive operator. So positive means if f is a positive function, that tf is a positive function. I don't say non-negative function. I don't like non-negative. So in function analysis, you call these kinds of operators positive operators, not non-negative operators. And these functions, positive functions. And if you want to stress that this function is never zero, then you call it a strictly positive function. Excuse me? Oh, okay. Maybe. Okay. So T is one preserving. So that means T maps 1 to 1. And the last one is integral preserving. So that T is S. T. S. T was dynamics, so S should be the general. Sorry for that. S should be integral preserving, so the integral here in y should be the same as the integral in x, the original. So that's a Markov operator. And Markov operators are the basic classes of operators that are important in general structural ergodic theory. Of course, Markov embeddings are special cases of Markov operators. Let me state a theorem or a lemma. About Markov operators. So Markov operators, they have good closure properties. So the first one is that if you take convex combinations of Markov operators, always, again, a Markov operator, that's easy. These are all convex conditions here. So convex combinations of Markov operators, composition of Markov operators lead to Markov operators. It's also easily checked. Positivity is obviously preserved under composition, one preserving also, and integral preserving also. It's easy to check that. So the second one is so a Markov operator is an operator on L1, so you can pass to the adjoint of this operator via the canonical duality between L1 and L infinity. And then you get an operator from L infinity here to L infinity of x. And this will also be positive and one preserving. So this will be one preserving because this one is integral preserving, and it will be integral preserving because the original one is one preserving. And then you can again extend this operator to an operator on L1. And so in a sense, the adjoint of a Markov operator is again a Markov operator. So this is originally on L1, on L-finity, but then by continuity, you can extend this to an operator on L1 spaces. Now, each Markov operator restricts to an LP contraction just by interpolation. So T from LP to LP, or S, is maybe S is an LP contraction. And in fact, so it leaves LP invariant, so in particular L2, and in ergodic theory it's very common to consider actually these operators on L2, because also on L2 the whole operator is determined as an operator on L2, and on L2 you have Hilbert space methods. Now then the set of Markov operators, which I denote by this, so these are the Markov operators. from L1 of x to L1 of y is closed in the weak operator topology. In the weak operator topology. That means weak operator topology means if you have a net and you have these kinds of well, I should write S here. T is dynamics. S F G for all F and G. So if you have this kind of duality and you know that this converges to this operator S for all F and G, and these are all Markov operators, then S is a Markov operator. So it's closed, and then that means that is compact in this weak operator topology. So okay, so these are the basic operators, the basic operator class. Now suppose you have a Markov embedding. Suppose you have a Markov embedding. Then, of course, you can, okay, then you know the following. You know that if you first take the embedding and then you take the adjoint, you get an operator on L1y. You first get here, then the adjoint goes back. This will be the identity, because J is an isometry on L2, for example, and on it's an L2 isometry as a Markov embedding. Then this just says that J is an operator, is an isometry on L2. So you see if.
So I don't understand what you said. What you just said is it's an isometry on L2.
Yeah, that means that this must be the identity for. Okay, I repeat the question. So I explain again why this identity is true. So J is an isometry on L2. So that means. Okay, even that, it's an isometry, then by polarization you get this. Yes? And then you bring this to the other side and then you see that JJ prime is the identity on L2 and then it must be the identity on L1. Okay, but the other way around, this is a projection. Just because this is the identity, so if you just plug this again here, then you cancel out one J prime J and you get this is a projection. This is a Markov projection, and a Markov projection, these are the conditional expectation operators. So this is just the conditional, this is the conditional expectation operator onto the range of J. So you might wonder, conditional expectation, you prove this usually by employing the Radon-Nikodym theorem. Well, if you think about the proof of the Radon-Nikodym theorem, one proof is just by using Hilbert space orthogonal projection method, and this is just that. So, okay, just as that remark.
If you have L2 random variables, not necessarily.
Excuse me, can you repeat the question?
It is necessarily, not necessarily you consider conditional expectation for L2 random variable or functions.
Yeah, but this.
You do not need square integrability.
Yes, you can continue it to L1, so it's because it's a Markov operator, it's positive and integral preserving, and then it.
Okay, L1. It's not a
Okay. Okay, so
sorry, you're getting still.
yes.
In general, is possible because it is positive.
Well, if you exactly you have positive and integral preserving, and then it is L1 contractive. Yes, because if you have a positive operator, then you always have this this inequality. This is just by positivity. And if it's integral preserving, then you integrate, and then you cancel out S, and then you have L1 contractivity, and then you extend. Okay. So the point now here is, suppose that is an embedding. It's not just an embedding as a factor. You have dynamics here. Then this conditional expectation here need not be T intertwining. So if J is intertwining, so then P, which is just this conditional expectation, need not be T intertwining. That's an annoying fact. Intertwining. I have problems with this kind of chalk here. Sorry. Twining. That means just that it commutes with T, with a dynamics. And then this conditional expectation need not be intertwining. That's an annoying aspect. It's not present if T is invertible dynamics. So if you only consider invertible dynamics, then you don't have this problem. But if you, by chance, also want to consider non-invertible dynamics, you have to be careful about this fact. And so intertwining for P with P is actually the same as let's say you have a weak intertwining property. But this is actually the same as to say that the range of P, so the probability subspace that is defined by this embedding is P invariant and is a T invariant and T prime invariant. So of course, if T is invertible, then T prime is just the inverse of T. So that means you have something that is invariant under the Z action that is defined by T. But if you're just interested in the forward actions, N actions, then you get a different notion of factor. That's what I want to say here. So you have a...
Your T is your S?
No, T is always my dynamics. So
okay.
J is my S here, so to speak. J is the... here I'm speaking about general Markov operators, but here I'm speaking about a Markov embedding.
So J is your dynamics. Okay.
Yeah. And the annoying fact is that if you have to distinguish clearly between a non-invertible setting and what is your category here, what is your notion of factor here, and what is if you have a invertible category, because you have different notion of factors here, one that are invariant under T and one that are invariant under T and its inverse, so to speak, if you have an invertible situation. And then if you want to have T and T prime invariance, which is somehow a hybrid notion, I would call it a strict factor. So it's also invariant under T prime. So for example, T need not be invertible so if just T is invertible on that factor, then this would be the case, for example. Okay. So these are the basic operator classes. So let me say something about topological models. So that's my next point, topological models. So there's a class of probability spaces that I consider as good enough that I'm, as a functional analyst, are really that I like them. These are compact probability spaces. So P is a compact probability space. X is a compact probability space. If, let's say, X is a compact Hausdorff space, and I will always assume Hausdorffness, and not mentioning it all the time. So compact, if I say it's compact, then I mean compact Hausdorff space. And the underlying measure is a Borel probability measure. Borel regular Borel measure. So these are the compact probability spaces. Now, if you have a general probability space, I call a compact model of it, a topological model of Y is a compact probability space together with a Markov embedding, with a Markov isomorphism, sorry. Yes, so now I'm building a subcategory of these spaces. Let's say I have L1 spaces, and this is an L1 space over a compact probability space, and I say, okay, I have a model. If I have an isomorphism, a Markov isomorphism of this L1x, where X is this compact model space, to the general given L1 of Y. And if I want dynamics involved, then I would, of course, I want to have that the dynamics is actually continuous dynamics here on X. So as that's the model, this is the non-dynamical notion, and with dynamics you would add that there's continuous dynamics on X. Intertwining, so phi is then, of course, intertwining. Okay, my time is almost up, so I'm getting at least to one interesting theorem here, namely the following. You can ask whether there are topological models. Of course, people experienced in this subject know, of course, about these topological models. So it's also common knowledge, but I repeat it here. So this is a theorem. Suppose you have any factor of a probability space. Okay, X is now just a probability space, not a compact one. So F is any probability subspace of such an L1 space, and maybe factor of the system. So if I'm taking a dynamical situation, factor of the system xt, and let A be a subalgebra let's say T invariant subalgebra, C star subalgebra of L infinity X, such that the closure, the L1 closure of A is actually our factor. This was one of the equivalences in the theorem that such thing always exists, but you can just intersect F with L infinity and you get such an algebra. But of course you can use smaller ones if convenient. Now let K be the Gelfand space of this C star algebra of A. This is the set of multiplicative homomorphisms of A into the complex numbers that preserve the unital homomorphisms as a C-star algebra, so to speak, into the complex numbers. And this is a space which is compact in the weak star topology. And Gelfand theory tells you that that you can find a C-star algebra isomorphism of C of k onto A. So this is hardcore functional analysis now. This is the Gelfand's theorem, or Gelfand-Naimark sometimes called. Although there is an argument that actually this is already in this first paper of Gelfand, which he has written alone and not with Naimark. So what I'm claiming is that you have an isomorphism here. Here you have the functional integration, the integration functional. You can pull this back to the C of k space, invoke the Riesz representation theorem to get a measure. And so there's a unique regular measure. So K is compact, yeah. Gelfand space, compact. Unique regular measure, measure mu on K, such that phi preserves the integral. Of course, always for all f in C of k here now. And this operator phi, of course, because it's measure preserving and it's positive, that comes out from the C-star algebra isomorphism property, is a Markov, proto-Markov operator. You can extend it by linearity, by linearity and continuity, by continuity to the whole L1 space. Phi extends to a Markov embedding to a Markov embedding, and the range of phi is just f. So this is the non-dynamical situation. If you add dynamics here, so if you add dynamics, then A should be invariant. So subalgebra, the T-invariant subalgebra, that means that the action of T on A can be pulled back to an action of an operator on C of k, but T is a C-star algebra homomorphism, so you get a C-star algebra homomorphism on C of k, and then also Gelfand theory tells you there must be an underlying continuous map that induces this action. So if A is T-invariant, there is a unique continuous function such that the Koopman operator on that of that dynamics here. So this dynamics, so phi intertwines this dynamics with the original one. So okay, this is basically it's Gelfand theory plus the Riesz representation theorem for the measure. Okay. Now, okay, maybe I have 1 more minute. Is that okay? Yeah. So the nice thing here in this theorem is, so first of all, what's the message? If f is actually equal to L1, then of course you get a topological model of L1, otherwise you get a topological model of a factor. And you see, it tells you that actually if you start with a general dynamics Markov isomorphism on an L1 space, you always find an isomorphic situation, functional analytically isomorphic, that has underlying dynamics. So that is a real Koopman operator, not just a formal one. So that should answer your question from before. The other aspect is you have a freedom in choice of these subalgebras. Usually there are many different subalgebras with the same property. Think of, you have the unit interval with the Lebesgue measure, and you have the continuous functions, and you have a lot of algebras, Riemann integrable functions, regulated functions, whatever. They're all algebras in between. But they all generate in the L1 sense the same space, L1 of the interval. So you have a lot of different choices for subalgebras here. So such models, such topological models are far from being canonical. There's one canonical one, that's the maximal one. That is if you take L infinity itself. That's the so-called stone model. So if A is L infinity X, then you call K the stone space of X, and that is a huge compact space. It's far from being metrizable, and that's the point. In many situations, like in ergodic theory, you actually want to work with you work with Polish spaces usually, or with probability measures on standard probability measures. Now, in this view, what is a standard? What is an L1 of X? How can you recognize an L1 of X such that you have a standard probability measure? Well, it's just that L1 of X is a separable Banach space. Banach has a dense countable set, and then, of course, if you are in such a situation that your space is actually separable, then you would like to have a K, not just any topological model, but you would like to have a metrizable topological model, because then, of course, you can invoke von Neumann's theorem on Polish spaces and standard probability spaces, and say that actually every Markov embedding between L1 spaces is induced by an underlying measure-preserving map. So on the class of Polish probability spaces, you have a complete one-to-one correspondence between state space dynamics and operator dynamics, but not if you widen the view to general L1 spaces. So maybe here's a little illustration just for the fun of it, what you can do with such things. This is actually old. Dieudonné already remarked this, and there was a following up paper by Holmosch and so on. So disintegration of measures. So how can you employ such things for a disintegration of measures? So take the following. Suppose you have your system X, T, dynamics. Actually, T is not important. So if you just want to have a disintegration, you just start with X. You have a factor, probability subspace. You have a conditional expectation operator. So that's the use conditional expectation onto F. Now choose so you have F and the whole space. Choose compatible models. Compatible means compatible models. What does that mean? That means, okay, you have a model K for so you have a model for the whole space, and you have a model for the factor. And now compatible means that your conditional expectation should map C of K. So if you pull back the operator, you should map the condition, C of k into C of L. You can always do this. Of course, for example, if you take stone spaces, then of course you have this, because that's just meaning that L infinity is mapped into L infinity. But if you are in a separable situation, you can actually find compatible models such that the C of k and the C of L are separable, and then k and L are metrizable. Because if a C of k space is a separable space, is a Banach space, the underlying compact space is metrizable. So you have a metric compact space. Now, what can we do with this? So you have, of course, this is an embedding. So the embedding of you have this embedding here. This is induced by this is a Koopman operator. So you get a continuous projection onto L. So this is a vibration of K onto fibers, and now these fibers are all closed because pi is continuous. And now you can just disintegrate your measure here by doing the following. So if you take any point in L, you have, of course, the Dirac measure at point L. Now, via this operator, you can pull this back to a probability measure here, invoking again the Riesz representation theorem. So you get mu y as the adjoint of P applied to the Dirac measure at y. And this is actually concentrated, has support on the fiber. So the support of uy is on the fiber for each y. And now I have to write it somewhere else, maybe here. Then it's not too far away from that side. So now if you have a function in C of k, then you can actually, so if you integrate this, well, what does that mean? Well, P is integral preserving as a conditional expectation. So you can write it like this, because P is integral preserving. But what does that mean? That just means that you integrate f against this measure, mu y. So this is just this. You see, and this is the disintegration. And it's a weakly star continuous disintegration. So the map that maps y to mu y as a map from L to the probability measures on K is weakly star, is continuous with respect to the weak star topology here, which makes it a compact space here. Yes? Now, this is, of course, you can do this with stone spaces, but suppose you have actually chosen compatible metrizable models here in the separable situation. Then you can, with this method, you can prove the general disintegration theorem for standard probability spaces, because you can choose models which have this nice property, then you disintegrate in the model situation, and then by von Neumann's theorem you can pull everything back, because you know that because of the model is also a Polish space, you have underlying state space maps, so you can pull this back. But the message is, of course, in general, you don't need this, so you can just work with the models right away. Of course, okay, I will stop here, and tomorrow I will continue with couplings and joinings there. Thank you very much.
Are there some questions and or remarks on this first lecture?
Yeah, this theory says more or less that forget original dynamic on the original phase space and study Markov operators and Koopman operators and so on. So the question is there a good description or characterization what really can be represented from original dynamics in the language, naturally represented in the language of these Koopman operators and Markov operators, and
so to answer this question in full generality, I would have to know a lot of things in mathematics. And actually, so I cannot do this. But at least for general theorems, this is a common procedure actually to exchange the underlying probability space. If you look into Glasner's book, for example, in many places he proves things where he says without loss of generality we can assume that the underlying space is compact or compact metrizable and so on. And this without loss of generality sometimes gives you a hard time at certain places in this book. But in general, it's this philosophy. Furstenberg applied it in his 1967 paper already, just in a little appendix note on the first section, I guess. And yes, in Tübingen they rediscovered it without knowing that Furstenberg had done this, because they didn't know this paper. But okay, it is a common. It's a common thing for structural. If you have structural theorems in ergodic theorem, then this you can do. And also to prove representation theorems, for example, so the Holmos von Neumann theorem on quasi-discrete spectrum. It's very convenient to use models directly, or the Hahn-Perry-Abramov theorem on quasi-discrete spectrum. That's now a work that I've done with my PhD student Nikita Moryakov. So one can directly apply these kind of model choosing and proving these old theorems on representation of such systems much more directly and I would say more coherently. So it's, of course, the result will not be changed. It's the same representation theorem, but it's a kind of a natural way to prove this by using these models. I don't know whether I really answered your question.
But there was no attempt to make some kind of general description of problems which
which are invariant under such models. You mean? So to my knowledge, you can see if you have a theorem, then you can actually guess whether this is. And you can see whether this is invariant under such things, because I can tell you which kind of which notions are of a functional analytic type. Almost everywhere notion, for example, is order convergence and these stuff. But if you, of course, use special features of the system, like you have a special dynamic system with of a combinatorical nature, then of course these kind of methods will not immediately tell you something, because of course you're forgetting a lot. So I mean, here only you have functional analytic structure, and all other structural properties that are present in a certain situation that you are interested in are not preserved in general, and you have to see whether you can do this.
Is it, does it make sense to talk about Feller in this kind of framework, in the sense that something that conserves also continuous functions, because everything is now in L1 and LP spaces, but I mean in probability theory it's
but then you somehow
sometimes
then you add a new structural feature, namely you add the function, the topological space that you're actually modeling, on which you're modeling. You incorporate this into your problem, so you cannot just. Then, of course, you can do this, but then the theorem will not be as general anymore. Then you have to incorporate what you actually are interested in, namely, you are interested in a special model that you already have. You have to incorporate this into the theorem. Yeah.
So here you have some functional analysis point of view for the meta-theoretical dynamic system. How do you think about the topological dynamic system?
Well, that topological dynamic system is even more direct, but here you don't lose information, because you see, if you have a topological situation, then if you have a topological situation, then you go right away to the Koopman operator. So you have a X compact, and you have a dynamics. Then of course you have Koopman operator on C of X, and here you have a complete one-to-one correspondence between continuous space-based dynamics and let's say the structure preserving maps on the functionalistic side. So you don't lose information.
You talk about isomorphism for factors?
No, it's the same. The only thing is you don't have. So factors is the same. I mean, here even the word factor is always correct. I mean, if you have suppose you have one. So you have y into x, and this would be a formal embedding. That means it's multiplicative. Preserves one, preserves the lattice structure, which is actually equivalent, and so on. Then it is induced by a factor map. So you have complete. So the functionalistic side and the underlying state space side here are in complete correspondence. So here you don't lose anything. So you can say, okay, why studying here instead of there? But I think here you have functional analytic, so you can have spectral theory. Yes, you have linearity, which you don't have here. And you have here a more general class of operators, namely also Markov operators, which generalize the embeddings. You have a spectral theory for Markov operators. You can look at invariant measures. Yes, so, okay, but somehow this side here, you can argue you don't gain much because somehow there are not null sets that you're forgetting. So the point here is that you actually the only thing that you're really forgetting here with this approach in the measure preserving case is just that you're forgetting about null sets, and that you actually say you can work with continuous functions always if you want. Because if you do stone models, if you have a stone model, yes, and if you have a stone model, let's say K is a stone model for a probability space X, then for the stone model you have this. So every L infinity function has a continuous representative. You can work with continuous functions if you like, but then of course this stone model is huge, it's totally disconnected. You don't have nice topological properties in a sense.
You said that your students can obtain the Abramov quasi.
Yeah. So we use these representation theorems to directly construct the isomorphism onto the compact group and this quasi-automorphism and so on. This affine automorphism. Mm-hmm.
Okay, so thank you very much.
Yeah, you're welcome.